Okay, so carbon dioxide emissions. This is a concern because if we add carbon dioxide to the atmosphere, it's going to increase the absorption of the infrared that's coming off the Earth. It's going to warm the Earth. It's going to exacerbate the good greenhouse effect, and we'll get the bad greenhouse effect. Currently, we're adding about 35 billion tons, which is 35 gigatons of CO2 to the atmosphere annually. Now, the Canadian contribution to that is relatively minor. It's about half a gigaton of carbon dioxide. Now, we're going to distinguish between carbon dioxide and equivalent carbon dioxide. This is the carbon dioxide plus the other gases that also absorb, things like methane and some of the refrigerant gases. So Canadians are responsible for 0.73 billion tons of that. So what's our per household equivalent carbon dioxide emissions? The E stands for equivalent. That means it includes the CO2 as well as the CH4 as well as the sulfur hexafluoride as well as the other refrigerants, So we've got 0.73 times 10 to the 9 tons, that's a gigaton, of CO2 equivalent. That's emitted nationally. And then, of course, there's about 12.99 million households in Canada. So this is annual emissions in Canada. And if you work that out, it works out to 56.2 tons of equivalent CO2 per household per year. So that is our annual emission, about 56 tons of carbon dioxide. And that is our share of, that's the direct energy we use to heat and light our homes, but also our share of the industrial activity, transportation activities, commercial activities, our share of all of those. Okay, so 56 tons per year. Now, why is this a concern? Well, first of all, we have data that shows us that the concentration of CO2 in the atmosphere is increasing. Okay, there's this famous graph measured in Hawaii, and we see an increase now, and we're up around 400 parts per million of CO2. Now, that's really small because, if we're 390 parts per million, to get to percentage, you divide by 10,000. So 390 parts per million means 0.039% by volume. Now, we've got about 50 years of data here, and we can see there's definitely an increase. We also see a seasonal variation. As the plants grow, they absorb carbon dioxide from the atmosphere, and the CO2 drops. Then as the leaves fall and as the grassy plants turn brown and they decompose, that carbon dioxide is emitted back. So that's the annual fluctuation. But anyhow, that Hawaii data goes back to about 1960. Before that, we can look at tree rings and check for growth. They can drill ice cores out of glaciers and go back in time, and there's tiny little bubbles of gas and locked up in the ice, and you can actually look at that gas, that's atmospheric gas, and you can measure the carbon dioxide content. And so if you go back in time, you find that, yes, it is true that, since the beginning of the Industrial Revolution, carbon dioxide concentrations in the atmosphere have gone up considerably. Now, if you go back in time, to millennial time, you'll see, there have been fluctuations in the past associated with the ice ages, etc., etc., etc. But certainly, since the time of the Industrial Revolution, carbon dioxide has definitely increased. And this is presumably due to human activity. Now, with more carbon dioxide going into the atmosphere, it's going to absorb more. We know that because a non-absorbing atmosphere would give us an Earth that was about 257 Kelvin. Our current atmosphere, which absorbs, and this is satellite data from the top of the atmosphere, we know there's missing energy here that's replaced by missing energy at these frequencies that's replaced by more energy at a bunch of other frequencies, so that the Earth, instead of looking like it's 257 Kelvin, minus 16 degrees, looks like it's 288 Kelvin, about 15 degrees. And that is largely due to carbon dioxide, because this big divot here is carbon dioxide. And also water vapor. Water vapor is actually the most significant of the greenhouse gases in the good greenhouse effect. So we expect that adding more CO2 is just going to enhance that. We don't have any direct evidence of it, but certainly it seems reasonable to say that. Now, there's a couple of challenges with that argument. The first challenge is that the amount of carbon dioxide is still vanishingly small. So water here, which varies, from 0 to 5% over the atmosphere, water, there's quite a significant amount of it, and it's responsible for about 3/4 of the good greenhouse effect. And you've got to go down here till you actually get to carbon dioxide. So we're adding a little bit more of a trace gas. Is that really going to affect planetary temperature? I mean, the models say yes, but this is quite a small number. We need to really understand why changing this small number would have such a large impact. The other challenge, of course, is that the release, that 35 billion tons of CO2, that flow is relatively small compared with the natural flows of CO2. We're talking about the natural fluctuations each year as plants grow and then die. And there's an equally large flow into and out of the ocean. This is like 10 times the flow that happens from burning fossil fuels. So with these huge natural flows going on, why does this relatively minor human flow matter so much? That's another challenge. The final challenge that we have is that with the amount of carbon dioxide we have in the atmosphere close to the Earth is already absorbing almost all of the infrared. Adding a bit more CO2 down here is not actually going to increase the absorption down here because it's already saturated. You won't absorb anymore. So if we add more CO2 and it's already saturated, maybe it's not going to have any effect. So those are the challenges that we need to address to explain why we should be concerned about carbon dioxide. The answers very simply are, number one, yes, it's small, but most of the water vapor is close to the Earth, and when you get up in the higher atmosphere, the carbon dioxide concentration is actually the most significant. The carbon dioxide is actually the most significant greenhouse gas. The counter argument here is, yes, it's smaller than these natural flows, but these natural flows have been balanced for millennia. This is brand new. This is upsetting the apple cart. The argument here is, yes, it's saturated close to the Earth, but carbon dioxide is very well mixed. So when you add carbon dioxide, we're adding carbon dioxide to the whole atmosphere, and that means that way up here, where the atmosphere was starting to get transparent earlier, it's now no longer transparent. It's now trapping energy, and that means we have to go to a higher elevation to get to the point where the atmosphere is transparent. That means there's more back radiation. That means there's a warmer Earth. Now, we earlier spoke about the difference between carbon dioxide and carbon dioxide equivalent. What we add into the carbon dioxide is the other gases that matter, like methane and sulfur hexafluoride and nitrous oxide, which is an important gas that comes from agricultural processes. Now, we can't exactly just add the volume or tonnage of methane to that because of the fact that there's relatively small amounts of methane in the atmosphere right now. If you add a bit of methane, it has a huge percentage change, or a much larger percentage change. So we introduce a quantity known as the global warming potential, which is just a multiplicative factor. For instance, for methane, it's 72. That means if you add a ton of methane, it's equivalent to adding 72 tons of carbon dioxide to the atmosphere. So it's just a ratio. It's the ratio of adding a kilogram of the gas in question, added up over 20 years, and then divide that by the effect of adding a kilogram of carbon dioxide over 20 years. Now, these ratios are assessed then on the basis of climate models. You add a bit of the gas, run your model over 20 years, and see how much of an impact that has on the Earth. So the values that we have currently that we're working with here is around 72 for methane and about 300 for nitrogen dioxide. These are refrigerant gases. The fluorocarbons have a really large global warming potential. So with our total emissions then, it was 56 tons per household. That's the total carbon dioxide equivalent emissions. That's how much we emit. How is it 56 tons? That seems like quite a lot. Well, a lot of it has to do with the fact, of course, that we consume energy to heat our homes, light our homes, heat water, run appliances, run our cars, and then make all of our stuff. And we can go through, now that we've tabulated our energy use, we can go through and tabulate our carbon dioxide use. It turns out, though, that the carbon dioxide is largely proportional to the energy use. So if you know that transportation takes about 30% of your energy, it's probably going to produce about 30% of your carbon dioxide as well. To be more specific, you need to look at your various fuels. So for instance, burning natural gas, this would be the chemical reaction. It's balanced, I think. 2 carbons, 4 hydrogens, 4 oxygens. Indeed, it's balanced. The stoichiometry tells us then if you burn 1 mole of methane, you're going to get 1 mole of carbon dioxide. And adding up 2 16s and 12, you get 44 grams of carbon dioxide that you've added to the atmosphere. Now, really, this oxygen was in the atmosphere already. So what you're adding to the atmosphere is the carbon. And that carbon's been buried underground for millennia, locked up in pockets of rock, right? Natural gas and petroleum, that's ancient carbon that was absorbed by plants from the atmosphere a long time ago. And we've talked earlier in the course about how if this is sort of biomass that you're burning, that was carbon that was just absorbed last year. So we're putting it back in the atmosphere. It doesn't really do anything to the atmospheric concentration. But when you're burning ancient carbon from rock formations under the ground, you are affecting the chemical composition of the atmosphere. Now, sometimes, since we're really only adding the carbon and the oxygen was already there, some people will use units of carbon. And if you add a mole of carbon dioxide to the atmosphere, you're really just adding a mole of carbon and the oxygen was already there. So 44 grams of carbon dioxide added, really the oxygen was there, and what you're adding is the carbon, 12 grams of carbon. So you need to pay attention to the units that they're using. Let's look at an example. Okay, all right, so here is methane, CH4. Natural gas is like 99% methane. So let's look at methane use, because lots of us use natural gas to heat our homes and heat water, and it's pretty extensively used in industrial processes as well, and also a lot in commercial space for heating. So when you burn methane, you get about 790 kilojoules per mole. So let's say you had an exajoule of methane, and let's see how much carbon dioxide you would get from it. Now, an exajoule is 1 times 10 to the power 18 joules. And so if you had that 1 times 10 to the 18 joules, we're going to first convert to moles, because the molar equivalent, we know that burning a mole of CH4 is going to give us 790 kilojoules, and kilo is 10 to the 3. So now we know an exajoule of methane is this number of moles. Now, we saw from our chemical reaction that you get a mole of carbon dioxide for every mole of methane that you burn, and by adding up CO2, we know there's 44 grams produced for every mole of carbon dioxide. So if you multiply this through, an exajoule of methane gives you 55.69 times 10 to the 12 grams of CO2. That's 10 to the 9 kilograms. That's 10 to the 6 tons. That's a megaton. So it's 55.69 million tons of CO2 from an exajoule of methane. Now, an exajoule is a lot of energy. In fact, the Canadian total for 2007 was 2.4 exajoules. That's the entire country, all processes, homes, industries, etc., etc. So let's see how much methane use that boils down to per household, or rather, let's see how much CO2 tonnage that boils down to. So there's the total methane usage. We know that each exajoule, when you burn it, of methane releases 55.69 million tons. And then on a per household basis, we know that there's 12.99 times 10 to the 6, or 12.99 mega households in Canada. At least there were in 2007. So the exajoule cancels. The meg is just clever. The 10 to the 6 is going to cancel. And I end up with tons of CO2 left as the unit. So it's 2.4 times 55.69 divided by 12.99. That's 10.3 tons per household due to burning of methane countrywide through all industries. And so you could see how we're going to get to about 56 tons, right? We already have about 10 tons due to the methane, and we still have the other fuels to consider as well. We still have the petroleum, and we still have the electricity that we used. So that was for methane. It was about 55.69 million tons per exajoule. You could show that equivalent units are a megaton per exajoule is the same as a ton per terajoule, or a kilogram per gigajoule, or a gram per megajoule. That's just casting out thousands. Now, we just derived this 55.69 figure from the molar heat of combustion of natural gas. In the book, we see that for petroleum, we have to make and coal, we make assumptions about the carbon content, and then we arrive at these values, these CO2 intensities. For electricity, we have to look at the mix in the grid because, of course, each source of electricity has a different carbon intensity, and we need to weight that by the amount of electricity we're actually getting from that source. And so the Canadian average, you'll see, really electricity has a greater carbon dioxide implication than natural gas does, and almost as much as petroleum. And the reason for that, of course, is the coal that we're using. Even though we're not making very much electricity from coal, coal still produces a tremendous amount of carbon dioxide on a percentage basis. So one of our priorities in Canada for reducing our carbon dioxide emissions should be to eliminate coal from the power sector, and then this number will drop precipitously. Okay, so let's look at an example for your household utility bills. Let's say you used 10,000 kilowatt hours of electricity and 120 gigajoules of natural gas in a year. So let's work out the carbon dioxide emissions associated with that energy use. So you've got 10,000 kilowatt hours of electricity, and we'll convert that to an energy. There is 3.6 million joules in a kilowatt hour. That's just a conversion between energy units. Then we'll look back at that chart on the previous page and see that there's 65.74 grams with the current Canadian grid of CO2 emitted for every megajoule of electricity we use. So now units, kilowatt hours cancel, megajoules cancel, we end up with grams CO2. So for the whole year, the electricity that you use is associated with the emission of 2.37 times 10 to the 6 grams. That's 10 to the 3 kilograms. That's tons. This is 2.37 tons of CO2. Now, earlier in the course, we talked about the fact that for hydroelectricity, a lot of that CO2 comes just when you build the dam. It's the concrete you're using in the dam. Same thing for nuclear power. For the other sources, for, say, natural gas turbines, or thermal natural gas, or coal thermal, those are grams of CO2 that are actually emitted when you're burning that fuel to make the electricity. Okay, in your house you also used 120 gigajoules of natural gas, and you just burned that. And from the chart on the previous page, we could see in our previous derivation, we know there were 55.69 kilograms of CO2 released for every gigajoule of natural gas. And so that boils down to 6682.8 kilograms of CO2, which is 6.68 tons of CO2. So now, for our household subtotal, we have, in our residence, used about 9.05 tons, or sorry, we've released about 9.05 tons of CO2 into the atmosphere. Now, for our total residential sector equivalent carbon dioxide emissions, we have to consider as well other gases that we're responsible for. You have to add First of all, our share of emissions of CH4 from our waste. And that means both our sewage and our garbage. And in the book, we show that that's about 21 million tons nationally. And then we also have to add our share of refrigerant gases. And not all of this, only a portion of this is used in the home, and in the book we estimate it to be about a megaton. So these two together work out to about 22 million tons nationally, or about 1.69 tons per household. So the total carbon dioxide equivalent emissions, we'll assume that you're an average house, and in addition to the 9.05 tons of carbon dioxide from your electricity and your natural gas, you add 1.69. So the total CO2e for this household is the 9.05 plus the 1.69 is about 10.74 tons of CO2e emissions. Now the average, as we show in the book, was 8.2 tons. So this house is using more electricity and natural gas than average. And here then is the breakdown for the average Canadian home, 56 tons per year. So residential was about 8. Our house that we just calculated was 10.7, but it's in the same ballpark. 12.5 of tons per household in the transportation sector. About half of that is your driving. The other half is trucking food from California, taking airplane rides, etc. 7 tons is our share of the commercial and institutional sector, the places that we work, the places that we shop. 6 tons from agricultural use, because there's a lot of emissions from animal sewage and also from fertilizers, and both the methane and the nitrous oxides have large global warming potentials. So that's why there's proportionally a much larger emission profile from agriculture, out of scale with its energy consumption. And then the biggest contributor, though, is the industrial sector and the power sector, the sector that gives us our electricity. So that's an introduction then to carbon dioxide and how much Canadians are putting in the air, and that's about 56 tons per household. And how do you get to your 56 tons? Well, we've talked about the various fuels, for instance, methane, then we looked at electricity, and obviously the petroleum that you're using to power your vehicles is another source. And we've talked about as well why this is a problem, because it's going to take the good greenhouse effect and enhance it and make it into the bad greenhouse effect.